Welcome back, guys. This is our lecture on series and parallel circuits. Let's get started. So, as a recap from last time, we've been talking about electric circuits as pathways from high concentration, the negative terminal of a battery, to low concentration. And we said that we needed to have a closed loop, a complete loop, for that pathway of the flow of electrons to occur. And so, as we go further, we have two overall methods of wiring up components in our circuits. The first is series, in which we have a single pathway for our electrons to flow. Our components are placed one after another sequentially. And then the second is in parallel. And you can see that here with our parallel circuit here, we actually have multiple pathways for electrons to flow. And you could say that this is one circuit here. Here's a parallel circuit to it, and a parallel circuit to that. So what we're looking at today is a little bit on the pros and cons of each type, and then how to go about analyzing these. Okay, especially what it means for our operation game. Okay, so starting with the series circuit, this is what our operation game is. A series circuit is one, as we said, where we have one overall pathway for electrons to flow through our devices and converting their electrical energy into the other types of energy that we want. The downside to this is if we have any break at all, right, say we throw a switch right here, then there's no longer a complete pathway for our electrons to flow. And so any single break in our circuit will cause the components to turn off. But if we think about that slightly differently, that tells us something a little bit more interesting maybe, which is if you put components in series, each component experiences the exact same electrical current. And electrical current has electrical energy. And so how much electrical current is really what analyzing our circuits is all about. Okay. And so current, we said in the past, is dependent from Ohm's law on the voltage and limited by the resistance. And so as you add more components in series, our resistance increases. And as a result, our current decreases. Why would that be? Well, think about our water analogy. Our battery is acting as a pump. And when we have, say, just one component added in series with our battery, our water is flowing from our pump, and then it reaches our component, which has more resistance in the wire. So we get to a little bit of a choke point, right? It's harder for the water to flow, and then it continues to flow through to back to the battery, right? If we have added a second and a third component, then now we've added more choke points to our pipe. It's harder for water to flow overall, and we get less electrical current. Okay, so when you add components in series, the resistance goes up, and as a result, the current goes down. If the current goes down, that means we have less electrical energy overall. Our light bulbs aren't going to be as bright. Our motors won't turn as fast, and maybe if we're talking about the desire to get things hot, we won't have our wires as hot. In fact, we'll have less thermal energy guaranteed if we have less electrical energy, less current. All right. What if we were to hook our batteries up one after the next? Well, as we'll see, if you put batteries end to end, positive to negative, if you put batteries sequentially in series, the voltage increases. All right, let's take a quick look at a series circuit simulation so we know what we're talking about. Okay, so it's not too bad. We see the upside of series circuits is really their simplicity. The downside is any single break in the circuit, we have all of our electricity stops flowing. Okay, so let's do a quick analysis as we go through our operation game. As we said, our operation game is a series circuit. So we said that if we added components in series, the total resistance increases. So we'd say our total down here for this circuit up here is R1 plus R2. Right? It's two choke points in our water analogy, making it harder for our water to flow. That's 10 plus 20 is 30 ohms. Not too bad. Okay, what if we were to add batteries end to end? If we were to add batteries end to end, this is like two pumps of water, one after the next. And each pump of water increases the pressure, right? So if you had two batteries end to end, positive to negative, then the voltage overall increases, and we'd have, this is battery 1, V1 plus V2. And we get 9 volts plus 9 volts equals 18 volts. Okay, this LED would become quite bright. If our pressure increases, meaning our voltage increases, then our electrical current will increase. Okay, let's give you guys an opportunity to practice this. So question 1 says calculate total resistance in the circuit to the right. Well, we have 1, 2, 3 resistors placed in series. Go ahead and give it an attempt. Okay, we have 20 ohms plus 50 plus 30. So we have 100 ohms of resistance. Not too bad. We have less electrical current overall if we place more and more components sequentially. Our conventional current is going to flow this way. There's one choke point. There's another choke point. There's another. Back to the battery. So what is the total current of the circuit to the right? Well, we know from Ohm's law, it's our total voltage divided by our total resistance. Our total voltage is 10 volts. Our total resistance is 100 ohms. So we have 0.1 amps. Okay, question 3, go ahead and attempt on your own. What's the current through each component? All right, well, it's actually the same for each of them, 0.1 amps. Why? Because here we have only one pathway for electrons to flow. If current is the flow of electrons, like water moving through a pipe, then it almost have the same amount of current. Okay, what if we were to wire things up in parallel instead? Because this is how we wire up our houses. You can turn off one light, as we saw in our classroom, and the other lights can remain on. And the upside to this is exactly that. You get more control. We have multiple pathways for our electrons to flow from high concentration, the negative terminal of the battery, to low concentration. All right. And so we'd say, yeah, a parallel circuit has devices and circuit forming branches. Each are a separate pathway for electrons. But the total current, something a little bit different happens here. Our total current is actually the sum of the current that goes through each of these components. So we think of, again, our analogy of water. Our battery is our pump. When we have just one component, just one resistor, or light bulb, or a motor, all components have resistance. Then our water can only flow in one path. But as soon as we have multiple pathways, our battery gives us our electrical push, and the water can flow down through this path, and through this path as well. All right, and so if you add more paths, then you have an easier time moving water, right? 2 narrow pipes for water to flow through is going to give you more water flowing overall than 1 narrow pipe, right? So if you have components in parallel, the total resistance goes down, and as a result, the total current goes up. Again, total resistance decreases. The only other thing is, our electrical pressure is the same across each branch. We said in the past that as soon as you connect a wire to a terminal of the battery, that entire wire gets the same electrical pressure as that terminal of the battery. Why? Because electrons want to spread out. Okay, let's go ahead and see a quick simulation of this so we know what we're looking at. Okay, so hopefully we can see that the total current was increasing and the total resistance is decreasing. All right, let's take a look at some examples. So here we have a parallel set of resistors. Our battery is, through convention, sending electricity this way, and we have 2 pathways. All right. In particular, as we can see in the simulation, the electrons here were moving faster than the electrons here and here. Why would that be the case? Well, our total current is equal to the current that goes through here and here. Right? 1 big pipe going to 2 small pipes. And so, how do we get to that? Well, we can look at our total resistance values. In this case, we got a funky equation. We have our total resistance is equal to 1 over R1 plus 1 over R2. In this case, we have 1 over 10 plus 1 over 10. And that becomes 1 over 2 over 10, which is equal to 5. Right? We see that our resistance is going down when we place our 2 components in parallel. All right, our batteries, if we place in parallel, we said that as soon as you connect a wire to either terminal of the battery, that entire wire gets the same electrical pressure because the electrons want to spread out. So if we put 2 batteries in parallel, the exact same thing occurs. But unlike in series, our voltage does not increase because we're in parallel and our electrons spread out, right? Our overall electrical pressure, when you connect 2 batteries like this, becomes the same. So our total voltage is equal to voltage 1, which is equal to voltage 2. All right, let's let you guys practice, and then we will be done for today. Question 1, calculate total resistance of the circuit to the right. All right, we'll help you out. We'll write the equation 1 over R1 plus 1 over R2 plus 1 over R3. All right, go ahead and give it an attempt. So we have 1 over 10 plus 1 over 10 plus 1 over 10, and we get 1 over 3 over 10, which ends up being 10 over 3. We get 3.33 ohms. We can see that our total resistance, when we added more components in parallel, has decreased overall. It's easier for electrons to flow because now we have 1, 2, 3 pathways. What's the total current of the circuit to the right? Well, to answer that, we use Ohm's law. We have voltage divided by our total resistance. So we have 10 volts divided by 3.3 ohms. So this should be approximately 3 amps. Question 3, what are the voltage drops across each component? Okay, to help you out, we have, as soon as this terminal of the battery is connected to this wire, we have this entire branch has the same voltage. That's 10 volts. Down here, same thing occurs. As soon as we have a wire connected to that terminal battery, we get the same voltage. So this is 0 volts. So our voltage drop across each branch is 10 volts. Okay, so we know the resistance of each branch. We know the voltage drop across each branch. So question 4 says, what is the current through each component? So this is the electrical pressure across each divided by the resistance. So you would just do 10 divided by 10, 10 divided by 10, 10 divided by 10. Okay, for each of those, we get 1 amp, which agrees with our overall total current of 3 amps. So what does this tell us? In our simulation, we saw that the current in this area near the battery was moving faster than over here. That tells us that the battery is supplying electric current for this branch right here, and this branch right here, and this branch right here. This wire over here is going to get hotter as a result of giving out more electric current, more electrical energy. All right, one last thing. Schematic diagram, something we're looking at going forward. We've already seen the symbol of the battery. Right? Our connecting wire is just a regular line. Open and closed switches are little levers to indicate breaks in our circuit. And then our most common one that we'll see a lot is resistance, understanding that every component has resistance. Okay. Going forward, next week we are going to be looking at combining resistors into compound circuits. So the reality is, you might want to have an LED in parallel with a motor and a buzzer. Right? Real world circuits are typically a combination of our series and parallel circuits. and we call those our compound circuits. But the reality is you can simplify our analysis. Say we have our LED is in parallel with our motor and our buzzer. Well, motor and buzzer have resistance. You can say together their total resistance is the sum of these two, and that's in parallel with the resistance of the LED. And so you can simplify your circuit down to just one total resistance value, and then you can use Ohm's law. Okay, so in summary, a series circuit is one in which components are connected one after the next. When we add things in series, the total resistance increases, the total current decreases. The downside is any opening will result in every component turning off. Our operation game is a series circuit. And our parallel circuit is one in which our components are placed in parallel, one after the next. If we have a break, they'll keep working. So our houses are wired up in parallel, so we can turn one light off and keep the others on. All right, that's it for now, guys. Good job. We'll see you next time. A little bit mathy, but we made it through it.